Alicia Bullock, and I am part of the TTSD QEP Corner. Today I will be talking to you about acid-base equilibrium. It is on chapter 10.3. The first thing that I have to say about acid-base equilibrium is you have to understand what an acid is, what a base is, and what equilibrium is. First, I would like to break that down for you. An acid is a substance that produces hydrogen plus ions when they dissolve into water. A base is an ionic compound that dissociates into a metal ion and a hydroxide ion when they dissolve into water, which is OH negative. Equilibrium is when no further changes have taken place in contraction between reactants and a product. Now, first, I have a question for you. The question is, now that you all have the definition of an acid, base, and equilibrium, I would like to go into depth about how an acid-base equilibrium goes about. First off, there are two reactants. There's one reaction that moves forward and another reaction that moves in a reverse and reverse. The forward reaction moves at a faster pace, and the reverse reaction moves at a slower pace. Now, when it goes from the reaction to the product side, it switches its position. So, the forward reaction that was once moving faster now becomes slower, and the slower reaction that was once moving faster. Now, we have to go in and talk about when the reaction becomes stressed. It is known as the Le Chatelier's principle. It states that the rate of the forward and the reverse reaction change to relieve the stress, and it reestablishes equilibrium. So the Le Chatelier's principle, I will show you what it looks like. It will look something like this. Let's say we have some water, and it is equally filled. All of this is the first part of the reaction. Now let's say it becomes stressed. I'm going to draw the same thing again. With it stressed, it will not be as equal as this. One can be higher while the other is lower. Since it is stressed, that is part of the Le Chatelier's principle. It will then go into back to normal equilibrium. It reestablishes its place. Now, with acid-base equilibrium, we have several acids and several bases. The most common acid and base is water. One of the most common acids that we have, you could say, is lemons. An acid is normally a bitter. It normally has a bitter taste to it. Has a sour taste, whereas a base has more of a bitter taste. A base would be like your common household chemicals, like we have bleach. Those would be considered that. Now, I am going to give you all a question. It comes from chapter 10, and it is number 2.1, just so you can understand what exactly an equilibrium is. Now, we have here the rate of a forward motion. The rate of a forward motion is 2 times as fast as the rate of the inverse reaction. Now, the question is this considered equilibrium or is it not equilibrium? This is not equilibrium because the forward motion is not 2 times as fast as the rate of the inverse reaction.
Hello, my name is Shanika Price, coming to you straight from the QEP corner with TTSD. And today I will be discussing with you chapter 10.5, the pH scale. Well, the pH scale is actually a scale that measures how acidic or basic a substance is. While the pH scale formally measures the activity of hydrogen ions in a substance or a solution, it is typically approximated as the concentration of hydrogen ions. However, this approximation is applicable only under low concentrations. And here's the pH scale, an example of the pH scale. The pH scale usually goes from 0 to 14, 0 being the most acidic, 7 being neutral, and 14 being the pure base. An example of an acidic solution would be lemon juice. Lemon juice is 2.2, so therefore it would be acidic because it goes from 0 to 7. Well, it's in between 0 and 7. H2O, which is water, would be neutral because it's a pure 7. And bleach is a 12.0 and it's between 7 and 14, so therefore it would be a pure basic. The way that you would measure a pH scale is H3O plus, which equals 10 to the negative pH. So it would either be negative 10 to the negative 9, 10 to the negative 7, 10 to the negative 5. And like I said, here's an example. Okay guys, now let's get to work. Now I'm going to give you a couple of solutions and you tell me whether it would be acidic, basic, or neutral. Now,
my bond that keeps it from meeting my intestine walls. Because you know I'm all about that base, low acid. I'm all about that base.
Hello, my name is Tiana Mills and I'm reporting live to you from QEP's Corner with TTSD. Today I'm here to talk to you about section 10.5, reactions in acids. For your stomach, Tums, anything, those would be considered as acid. Anything that could be considered as a base would be household cleaning supplies such as ammonium. Household ammonium, something to clean your mirrors. Acids react to certain metals to produce a hydrogen gas, a salt, or water. There are metals that react with acids such as potassium, sodium, calcium, magnesium, aluminum, zinc, tin, and iron. These are single replacement reactions. So now I have a problem for you all. My problem is first we would start off with step 1. And step 1 is the given step. So what you have given should go in step 1. Or what you need should go in step 1. So what we have given is 35 milliliters of hydrogen chlorine solution. We have 37.5 milliliters of 0.86 molarity of NaOH solution, and we need the molarity of HCl solution. So then next you will start off with step 2, which is your conversion section. So your conversion is 1 liter of NaOH solution over 1,000 milliliters of NaOH. Then you have 1 liter of NaOH solution over 0.85 moles of NaOH. Then you would have 1 mole of HCl over 1 mole of NaOH. Then step 3, you put everything all together. You have 37.5 milliliters of NaOH solution times 1 liter of NaOH solution over 1,000 milliliters of NaOH. 1,000 milliliters over NaOH solution. You would multiply that by 0.186 mole of NaOH. Then You will put that over 1 liter of NaOH solution, and you will multiply that by 1 mole of HCl over 1 mole of NaOH, and that would come out to be 0.00697 moles of HCl. Your next step would be to find the molarity of HCl solution. So to do that, you would have to do moles of HCl, since that's what we need. And since we need to find the molarity of HCl, we would have what we need at the top. So you would have the molarity of HCl at the top. So, no, you have the mole of HCl at the top. So you have 0.00697 mole of HCl over 0.035 liters of solution. And that will come out to be 0.99 m HCl solution.
About that bass, no acid. I'm all about that bass, about that bass, no acid. I'm all about that bass, about that bass.
Hi, my name is Taylor Bradshaw, part of the QEP Corner TTSD, and I did mine on 10.7 buffers. A buffer solution maintains pH by neutralizing small amounts of added acid or base. In a buffer, an acid must be present to react with any OH with added, and a base must be present to react with any added H3O. The acid and base cannot neutralize each other, therefore, a combination of the acid-base conjugate pair is used to prepare a buffer. Most buffers have a weak base and salt containing its conjugate acid. Here's a problem for you guys. Which of the four is a weak acid?